The second part of this exercise is about the locus, so let's have a look at that now. The locus of a hyperbola. So we know if the worded description for the locus of a point pxy that forms an ellipse is that the distance of the point P to a point A plus the distance of the point P to another point B is c units, what is the description for the locus of a hyperbola? Here's my point moving in the diagram along the hyperbola with my two focus points A and B, or F1 and F2. It doesn't matter what width or how large my hyperbola is, there's still some kind of relationship between the distance of my 2 points to the point P. Hopefully the equation of an ellipse will help us figure this out. So the equation of an ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1. The equation for a hyperbola we now know is x minus h squared over a squared minus y minus k squared over b squared equals 1. That is the only thing that differs between these two equations, the plus and the minus. So the locus wording is pretty much the same with a little bit of difference. It's actually the distance of P to a point A minus the distance of P to a point B equals c units. So the only difference here is we have a negative in between rather than a positive. First example. Find the locus of point P if the point moves such that the difference in its distance from two fixed points A and B is 6 units. I'm going to write this a little more simply using words and then mathematical notation. So I first have the distance of Px to a point A 40. Then remember we have this difference here, or basically this subtraction. So we put in our minus sign. The distance from P to now B. And we know that all of this is equal to 6 units. Okay, great. I've got a very clear representation of what I'm trying to write. So now I know the distance formula from xy to A, and I also know the distance formula of xy to B. Simplify a little bit, we'll have the square root of x minus 4 squared plus y squared minus, under our square root, we have x plus 4 for the b plus y squared. We can just get rid of the zeros there, and that all equals 6. Once we've done the mathematical notation version, we've got to rearrange this in the form of a hyperbola. So you might like to write down the general form of a hyperbola just to give you a sense of direction about what you're trying to make this equation look like. And if you're not sure what it is, it's on the side there. I couldn't quite fit it in. The first thing I want to do is not square both sides just yet. I want to make my squaring easy. So I'm going to move the second square root to the right-hand side. That way I get a plus, and that way when I square both sides, it's easier to manipulate. So let's square both sides. On the left-hand side, we just get rid of the square root sign. On the right-hand side, it's a little bit more complicated. Remember, this is what we're really doing. So first we do 6 times 6, that's 36. We're going to have 6 times everything in our square root, plus another 6 times everything in our square root. So that will give me 12 times everything in our square root. Lastly, I'll have the square root times the square root. Again, the square roots will just disappear here. So this is the nice part. Next, let's expand where we can, and then hopefully some things will cancel out from both sides of the equation. And I just drew a massive x squared. I'm going to redraw that. On the left-hand side, if we expand the brackets, we get x squared minus 8x plus 16 plus y squared equals, on the right-hand side, I'm just going to move things around a little bit. So I'll get 36. Then I'm going to expand my x plus 4 squared plus y squared there. And I'm going to leave my square root as the last component of that equation. What can we see? The y squares will cancel, the x squares will cancel, the 16s will cancel. All right, this is good. I'm going to move that plus 8x from the right-hand side to the left-hand side by subtracting, and I'm also going to move that 36 across by subtracting. I'm going to leave the 12 and the square root on the right-hand side. So if I do that, I get minus 16x minus 36 equals positive 12 times the square root. I'm going to divide through by a minus 4. It'll just make the next few steps easier and the numbers not quite as big to work with. On the left-hand side, I'll get 4x plus 9. Divide 12 by negative 4, I'll get minus 3, and my square root remains the same. Now, remember that my equation of a hyperbola doesn't have a square root in it, so I'm going to have to square again. Be careful with this step. It's easy to make arithmetic errors. I would know. On the left-hand side, we get 16x squared plus 72x plus 81. And that's going to be equal to, so square minus 3, that's just 9. And then remember, multiply that 9 by, or remove the square root, x plus 4 squared plus y squared. I like to do the inside of this big bracket first, and then multiply through by 9, just to, again, minimize my errors. And we see some nice things pop up here. What can cancel? We have the 72x's, they'll definitely cancel. Now I'm going to bring my x squareds to one side and also my y squared to that side, because remember, the equation of a hyperbola has the x's and the y's on one side and then a 1 or a number on the right hand side. So let's move all the numbers, all the constants to the right. I'll end up with 7x squared minus 9y squared equals 63. This is good, except remember, for a hyperbola, we have a 1 on the right-hand side. So divide both sides by, you guessed it, 63. And I've got the minus in there, which is great. When I divide by 63, things will hopefully cancel out for us. And they do. I get x squared over 9 minus y squared over 7 equals 1. End of problem and end of the slides. So if you ever need a little wisdom, you can always trust Gandalf with small acts of kindness and love.